Okay guys, so we are now reaching to the control of the robots after a semester of teaching you heavy mathematics almost. So here in the previous class, part 21 I think, right? If I'm not wrong. So I have a 2 degree of freedom robotic manipulator in the plane. So, and you see that we had the mass matrix or inertia matrix. See that has a component of A1, A2, A2, A3. And C1, C2, C3, C4. So I'm gonna just see properties because it's too much in this level of undergraduate. And this is the Coriolis matrix, that's right. This is C and Q dot, that's right. And the B is the gravity matrix, B1 and B2 and vector, I'm sorry. So I said this is the control input, just some stupid things to just make a simulation if you remember from the previous class. But now this class, I'm gonna fix this and design the PID controller to push the robot to the set point that we want to go, okay? And it's the right hand side, as in the previous class, inverse of M, tau, torque vector, and the C Coriolis matrix, Q dot, minus G. And this is the state variables. And if you see here that I have done, and I run it again, so you're gonna see by giving some funny harmonic torque, okay? This is what we're gonna get. Just bear with me. See, this is the blue line. This line is for the theta 1, and this is for theta 2. That is funny, but we use the robots, okay, to pick up items, like as I'm gonna show you in like back in Matlab that we have done many control algorithms experiment on that. So this was our robot, that's right. Let me fresh remind. So here was theta 1, and today I'm gonna design controller and make simulation of that and make movie by Matlab. Making movie is very important, okay? Here was L1, L2, M1, M2 that we define in the Matlab code, as you see here. M1, L1, L2, L2, and this is the gravity, that's right. And we ended up by the Lagrangian equation to M matrix M or inertial matrix theta double dot, both faces, this is vector, plus C Coriolis matrix, that is a function of theta and theta dot, that's right. In theta dot, this is both faces, this is vector, plus G of theta, that's right. So this is gravity is equal to torque. This is the bold faces because it's vector. Because as you see, bold face theta, it is vector of theta 1 and theta 2. We did in the previous classes, right? And the torque is, if I say this, bold faces, it is U1 and the U2. These are the torques that we are applying on this joint, U1, and on this joint to push theta 1 to a desired trajectory or set point and theta 2 at desired trajectory. So what I want to do, I want to say theta 1d goes to 45 degree. Again, in the coding you have to write in radians, right? And I'm gonna this is desired angle of the length to, I want to go to pi over 30. This is 60 degree, I mean. This is 45 degree, huh? So, but for pushing this, I need a controller. In the previous class, I did like this. Remember, theta double dot from here was inverse of mass matrix. Remember, tau, right, minus C theta dot plus minus G. Now it is time I go to undergraduate or ME530 controller system modeling that I'm teaching in SDSU. And now I'm gonna say, you know what? Your tau is PD controller, is PD controller. For refreshing your mind, PD controller, we are writing as, remember, KP proportional gain in E error signal, right, plus KD derivative, because this is for derivative, this is for proportionals, right, KD in E dot, right? But you see that E is bold faces. Why? Because we have two E. This is the vector. It is for error signal of the joint 1, error signal of joint 2. So it's going to be E1 and E2. Right? If you have two link, you're going to have your error signal going to be a vector of 3 by 1. If you have n joints, you're going to have a error vector of n by 1. This is 2 by 1. So, but we know that at the end of the day, as you see in this figure, this is U1 and U2. So to make this happen, your KP gonna be a vector of, yes, 2 by 2, gonna be KP1, 0, 0, KP2. The diagonal gain of proportional gain, 2 by 2. Now, 2 by 2 multiplied by 2 by 1 gives you 2 by 1. The same is KD, derivative matrix coefficient, gonna be KD1, 0, diagonal, KD2. This is 2 by 2. So now I have to modify my controller. Why? Because if I put this here, it won't give me whatever I want. I'm going to teach you right now. I'm going to say, let me go to the next page. I'm going to say PD is good, but not in this format. Why? Why is here? Guys, this is how I developed this, right, in the previous class. Theta double dot is m minus 1 tau minus c theta dot minus g gravity. If I implement this tau, that is kp theta, I'm sorry, e plus kd e dot. By the way, you know, I didn't teach you here, but I'm teaching you because maybe you forgot. E is the difference between E is the difference between the real theta that is happening minus desirable theta. So on the other hand, your E, the capital E here, as I said, that you have E1 and E2, gonna be this right? Theta 1 minus theta 1d, as I said here. How much is that? Pi over 4, right? And theta 2 minus theta 2 dot d. Yes or no? So E dot, both faces, gonna be theta dot 1, right? And theta dot 2, because these are the constant numbers here. Their derivative is 0. Their derivative is 0. That's right. Understand? So now, if I implement this here, what you get is this. Theta double dot is m inverse kpe plus kd e dot minus c theta dot plus g, right? But you cannot judge about the stability of the system. That's right, this equation. So that's why I'm revising the PID controller to this term. You have to do in any robotic problem if you want to implement the PD controller. You're gonna say it's gonna be m. It's gonna be m, right? KPE plus KD E dot plus C Coriolis theta dot plus G. And when you apply the PD controller for the robotic systems, always use this modified PD controller. Reason? We have mathematics. How? I'm just gonna implement this torque or the control input inside here. Let us do that together. So what you're gonna have, theta dot gonna be m. Oh, sorry, I forgot this. And you have here. Sorry. Let me plus theta double dot, this is bold faces, means you have vector of r, the acceleration of the desired trajectory. So dot, I say d, the acceleration of desired trajectory, right? And now plus c theta dot plus g. Okay, why I'm doing this? When you're applying, even that the default controller of my Baxter in the lab is the PD controller. When I'm adding this term, means that I'm compensating the gravity and the Coriolis term to be eliminated from my equation. How? Like this. Look at here. Now I'm writing about this. Theta double dot is m minus 1. I'm now implementing this tau here. Look at here. I'm just do nothing but just put tau here. M kpe plus kd e dot plus theta double dot d, here we go, plus c theta dot, I just implemented, plus g. Now here you have another one, minus c theta dot plus g, minus g, that's right, minus g. Here we go. Now you see that simply I eliminated the computation of these together. They go to New York, right? Remaining is this. Theta double dot, this is bold faces, means that your vector is equal to m minus 1 m kp e, this is PD part, that's right, kd e dot plus theta double dot d. What is this? Any matrix multiplied by its inverse is unit identity matrix, right? Unity matrix. So what you're gonna have, theta double dot is equal to kpe plus, assuming that all of them they are bold faces, okay? I'm just double emphasizing, and this is the matrix. This is the matrix, right? Plus theta double dot d. Understand? And sorry guys, I have to define this another way. The d is theta d minus theta real that is happening. Okay, so it's gonna be 1d, yes, because it doesn't work like that. This is 1 real, this is 1, I mean, and this is 2d. Just I switch the places. This is how I define it, right? And 2, based on what I defined here. So now, guys, look at this. Let me change the color. Let me change the color. If your E is this, your E dot gonna be theta dot D minus theta dot. That's right. So come down here. If I take another derivative, gonna be E double dot, gonna be theta double dot D minus theta dot. Yes or no? So if I now move this to this side, what I get is this, guys. Theta double dot D minus theta dot plus, this is matrix KD E dot plus KP matrix, this is vector E is equal to 0. What is this? As I said, this is E double dot. At the end of the day, we get our famous equation. Let me change the color. Gonna be E, this is bold faces, means vector E double dot plus K D E dot plus K P E is 0. Have you seen this? Yes, million times. I taught in the vibration, undergraduate control, system modeling and analysis. So this is second order, and it has two poles that can be under damp, over damp, or critically damp. How? This is how you tune that, right? Suppose this is single scalar terms, right? So see, this is how we tune the PD coefficients. This is KD E dot plus K, because they are decoupled, that's right. E is 0. And this is diagonal matrix. Suppose that, and this is diagonal matrix, so we can decouple them. So now, suppose this is a scalar equation. Remember, if you compare this with our famous relation I taught in the vibration undergraduate control, that was, say, x double dot, remember, mass spring damper, plus 2 zeta omega n x, remember, plus omega n square x dot, x is 0. That's right, remember? It was the damping ratio and omega n. Now we can say, okay, I want to have the robot to be under damp. Behavior under damp means it has a peak, that's right, and oscillation. That's funny, that sucks. Means that you want to have zeta smaller than 1. That's right. Or you're going to say, I want to have a critically damp. That is very good for robotics because you don't have any oscillation. But you don't want to have the over damp. That's right, because this is too slow. So in the most robotic system, we want to have the critically damp response. Right? If the zeta is 1, so you're going to have 2 omega n, and here you have omega n square. So here you say, by comparing this with this, you say KD is 2 zeta omega n. That's right. If you say, if you want to have the critically damped system, it's going to be 2 omega n. That's right. And your KP going to be omega n square. Right? And now you can tune that. Understand? So it's enough that you say, as for example, omega n is 1, so Kp gonna be 1 and Kd gonna be 2. This is how we tune that for computer. So let us go to Matlab and implement these one by one, and I make a simulation and make a movie of the robot that is moving. Okay, so now we have to, and I'm gonna plot everything, and I'm gonna make a movie by this. So as I said, your tau is equal to m multiplied by, see here, exactly what I'm writing. I'm writing this equation, exactly this. So m multiplied by Kp multiplied by E, I'm going to define all of them one by one, plus Kd multiplied by E dot, I'm going to define all of them, plus Dd theta. See, Dd means second time derivative, here we go, plus look at here, C theta dot plus Q, we have it here, plus this is that we have C theta dot, we got that, plus G, here we said, I said Q, I'm sorry, G, so this is G. So this, if you implement this here, C theta and it goes to the hell, that's right, remaining is this. So now we are designing modified PID controllers, right? So this is our new theta, but we have to define, let me delete this because you're going to confuse. Please type this, okay? Type this. MK. But you have, as I said, this is decoupled, okay? It's a diagonal. I'm going to say KP1, 0, as I said here, and 0, K, P2. Here we go. And let me put, oh, why this is KP1. So they can be distinct. That's right. This is diagonal proportional matrix gain. That's right. And this is KD. See, we need KD also. It's KD1 and KD2. Now I'm giving some, I don't know, based on whatever I set here. See here, based on I want to have the critically damped system, huh? Come on. Based on whatever I judged here, say omega n is 1, and so this is gonna be 1. So KP gonna be 1 and KD gonna be 2. So I'm gonna select all of them equal. So I say KP is equal to, what was that I got? KP gonna be 1, just equal, huh? But you can make it different. KP2 is equal to 1, but this must give you critically damped response for the robot. But you can play with them. KD1 gonna be 2 based on whatever I designed, and KD2 gonna be 2. So this set must gives you, based on whatever I derived from the combining with the vibration course on the graduate control, this is gonna give you, right? Because zeta is 1, it's critically damped system. So 2 omega 1. So if you come omega 1, it's gonna be this. That's right, critically damped system. So, and KD2. So now we have KP and KD done, but we have to define E, error signal. Error signal, as I told you, look at here, is theta desired minus theta real. So I said, so you have 2. So you have, so E1 is equal to theta desired. Say, let me first define this. So theta 1 desired is pi over 4, as I said. Theta 2 desired is pi over 3. Okay, I'm just making everything based on code. So this is gonna be theta desired. So E1 gonna be theta 1 desired. That's right. Theta 1 desired. Minus real. What is real? Your state variable M1. That's right. M1. Here we go. Now E2, I'm just copying and pasting to save time. Oh, what the fun is this? Oh my god, there is some bug in my keypad. So E2, come on. What is this? I have to use this, sorry guys. And this is E2, so theta 2D is gonna be E2. So I just have to now, okay, I'm sorry. So unreal value is theta 3. You got the state equations, theta 3, so M3. That's right, M3. So now I have to make a vector of this because this is vector. So now your E error signal is E underline 1, E underline 2. You can extend this to a 3 degree of freedom, 4 degree of freedom, 5 degree of freedom, 6 degree of freedom, or 7 degree of freedom that right now Baxter in Matlab works by default of PD controller. Okay? And my PhD students, they are doing that for different nonlinear controllers. So we made this. So we have KP matrix, E is, so now you have to have E dot. That's right. So E dot, I'm just copying, pasting. This is very important, guys. Just focus, okay? Control. So E dot, I'm gonna say DE1, DE2, because we need DE, that's right? So obviously you see that time derivative of a constant number is 0. Time derivative of another constant is 0. So, but time derivative of M1, your state variables, guys, is M2. Time derivative of M1 is M2. Look at here. Okay, so don't put it this like that. Time derivative of M3 is, M4. Here we go. We did it. Now you can say DE, because you're gonna use in your controller. DE is equal to DE underline 1 and DE underline DE underline 2, right? We have M, you have KP, we have what's happening? Let me use my pen. We have M, we have KP, we have E, we have KD, we have DE plus. Now, obviously, this desirable angular acceleration, because your desirable, this is a constant number, so I'm gonna say, see here, I'm just copy paste. Theta double that, that's right, desired. So, oh my god. Okay, so D. So obviously, theta double dot desired, and I'm gonna say desired. See, here is desired. Look at here, where we are. It's recording, yes. Where is that? Yeah, here's desired. See, this there, that's right. So first of all, I have to revise it here because it's gonna make it confused. Theta double dot theta desired. I'm gonna name like this. So obviously theta desired of a constant number, second time derivative is 0. And now the same for here, gonna be 0. I'm gonna say desired. And now, but I need this to put it here, so it is vectors, right? This is vector. So I'm gonna, oh my god, desired is DDE underline 1D and yes, finally worked. And this. Now we have everything, that's right. Oh, this is desired. You have a D here. See this there. And now I made my controller. And I made my controller. Right? M I have, KP I have, you see here. E I have, KD I have. And I designed this based on the graduate control and vibration to give you critically damped response, right? But you can't change them. Desired I have, and these are 0, minus M4, M3, and this. And now, okay, now I can, let me see what I can do. Now, based on what the control I designed, I said that, where are you? I want that the first link goes to 45 degrees, the second link goes to 60 degrees. Huh? Let's do that. Let me see if it goes. Oh yes, it goes. The first link goes to 45 degrees by the PID modified PD controller, and the second goes to 60 degrees. And now it's interesting, that's right. Let me now make it more sexy. Width, line, width, and 2. Because this is the conclusion of this course. I'm gonna say X label is time in second. Please do at home what I'm doing. So and shift control paste, and Y label is what? Obviously theta in what? In degree, right? Here we go. If I run this, do I have any typo here? yeah, line. Here we go. See, this is theta degree and time, and the first link goes to 45 degree in 10 seconds. This, and the response is you tell me is critically damped, because there is no oscillation like this, right? And we don't want to have it in vibration. That sucks in in robotics. So we don't have such oscillation. We have critically damped response. So we designed controller for the robotic system. And now we can say, you know what, I'm gonna have a global parameters. I'm gonna say con, I'm gonna say y, because I'm gonna plot these torques. You see that which torque push you to desired. I'm gonna say okay, I'm gonna say u1 is tau, because this is 2 by 1, that's right, 1 and 1. This is the torque that it drives the first joint, and the u2 is torque of 2 and 1, that's right. This is that's it. So now you're gonna say, I'm gonna make a vector of them. See, con. Bear with me, I'm gonna teach you. Con. Then when you define u1 and u2, you're gonna make them, this con is there, means counter. So u underline 1, u underline 2. I'm gonna plot them. Bear with me. Okay, the control inputs. The robotics is good, but if you cannot control the robot arm, you have to go and sell, I don't know, burgers. Okay, you're not engineer anymore. So then you're gonna say, make a counter for me. Con plus 1. This is how so now you go to the solver. Okay, again you're gonna copy and paste them here, this command. Make it global variable. It calls and knows everywhere in every Matlab code. So you're gonna say con is equal to 0. When it starts from 0, goes to OD. When it runs, add to con 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then by putting that, you're gonna make a vector of the torques. This is beautiful, right? So now I can plot them. How? Just copy and paste. I'm gonna say, so let me run this, because I want that you know why I'm doing this. Okay, this is u underline 1. This is u underline 2. Now it's a vector. Okay, so here gonna be u1, obviously the legend, the control input that drives the robot. This is gonna be u2. It's gonna be u2. That's right. And this is u. Total means that you have 2 u's. That's right. What do you expect when I run this? Because your time step is not the same with the ODE. It's gonna give you for the figure 2. The solution is this, guys. You're gonna say, because this time step is not the same with the ODE solver, because ODE solver is flexible. So because of the mathematical things, I'm skip that. Just learn from me. Okay. So where we are. Oh, u1. You're gonna say time that exactly is doing for the ODE solver. Con is t, this t that is using for the ODE. So here you're gonna say again time. You're gonna here again say, you're gonna hear time. So now you're gonna use this time and time. Now, and if I solve it, it comes up, no doubt. You see, this is the control torque for driving the first joint of the robot, and it's not degree because this is torque. This is Newton meter. Newton meter, right? It's torque applying to the joint. So this is the and this is for the second joint. Understand? And it's, hey, you are engineer. You are not I don't know, whatever. Okay, when you look at these guys, when you look at these, okay, okay, your joint of first link must take higher torque. Why? Because it's carrying the second link, that's right. So the weight of the second link is on the first link at least. So its dynamic is on the first link. So the torque of the first joint must be higher than the torque of the second joint. Clear? This is not by accident. This is reality. Okay? Okay, now we plotted that. And we have the critical dam robotic system. Now I want to make a movie. Okay, how? It's very easy. You're going to say for K from 1 to 1. Okay, length of time, total time, this time, this is total time, because you have vectors, right? What the, okay, total time, I'm gonna say figure 3 because we already have figure, and you have end here, obviously. Figure 3, but you have figure 1 here and figure 2 here. Now you're gonna say this command. Okay guys, let me show it here first because it's too much for you. Guys, if you want to plot this in Matlab, make a movie, you have to give x and y of this point and x and y of this point, and then x of y of this point and x of y of this point. This is how you plot a line in Matlab. So x and y of this point is 0 and 0. That's right. But what is x of y of this point? Let me show it here. It is L1. That's right. Cosine theta 1 and L1 sine theta 1. Yes or no? This is trigonometry. That's right. So this is the command that we use in Matlab for plotting this line. Plot bracket x of this point, x of this point is 0, semicolon, x of that point is L1 cosine theta 1. This is how we do. And y of this point, these are x. Y of this point is 0, and y of that point is how much? L1 sine theta 1. Unless you say black line, sorry, blue, with the blue color. That's right. So these are x's, these are y's, and now you plot that line. But your theta 1, based on the Matlab code, is y, the first column. That's right, theta 1. Now let me go exactly to the Matlab. Okay, so I taught you the basics of the robotics. I taught you how to design a modified PD controller, and now you're learning how to plot that. Gonna be 0, L1. Because we don't have L1, you can add it here. From where? From global variable. Because right, where are you? L1. Because you can add also from here because you already defined L1. That's right. See, you already defined here. Same for L2, that's right. L2, because we need that. And here you're gonna have L2. So here you're gonna have L1 multiplied by cosine of what? Your first is M1, angle of state variable, y of first column and all the rows. But you are, let me finish this first. Okay, this is x as I wrote here, but you need a counter here, so not all of them, because you're gonna make a movie. K 1 1 1 2 3 4 5 6, all the rows. Okay, please do it at home and you will figure out. And now let's go to y's. These are y's, as I said, 0 and sine this, right? Here we go. Now you plot that, but I'm gonna say it blue, and the line would be 2. Here we go. And I have to put a bracket. So to make it visible, first let me make a movie from that. I'm gonna say axis is from 0 and what is the length of the first link? Is 0.6.62. I'm gonna say 1.5 and 0 and 1.5. Right? Sorry guys. So let me show you. First let's debug it, so there is some typo. Oh, I forgot this bracket here. Okay. What's wrong? Oh, lengths. What's with this, huh? Hold on. Okay. I have a typo in this. See, I have to go to kindergarten. So, oh, yes. You see that? I made a movie of that for the first link. Goes to, and it's figure 2 and figure 1. I already defined this, right? So you see that I went to 45 degrees. See? 0.1, 0.5, 45. Now I can change it. I'm going to, because I made the code. I'm going to say, you know what? Go to 60 degree. It will go. No doubt. This is science. This is not fiction. Yes, goes to 60. Now I can say, you know what? Goes to, please go to 80 degrees. So 85 degrees. See, divided by pi 180. Everything must be based on the radian when you're coding. When you're plotting, you can change it to degree to see it. See, you can change it to degree. See, it goes, no doubt. Oh yes, it goes. See, so now, see, now I want to plot the second link of the row. Second link, I have to give the xy on this and xy on this. Obviously x, let me delete this because you don't need this anymore. What are the xy of the second link end points? This is trigonometry from high school. This is not robotic course. So xy of this point is this plus this, as we did previously. Remember, for deriving the Lagrangian equation, gonna be L1 cosine theta 1 plus L2 cosine, as we did, theta 1 plus theta 2. Remember, theta 1 plus theta 2. This is x of that, and the y of that gonna be L1 sine theta 1 plus L2. Remember, for kinetic energy, theta 1 plus theta 2. Now I'm gonna use again the plot command for plotting second, and let's do together. I'm gonna copy paste this, for God's sake, here. But before doing that, because you are plotting together, you have to put the hold on. You're gonna say to Matlab, please hold on, hold on. Okay, so now I'm gonna paste it here. So this is your new x, and the y of the second end of the second link, as I said, I'm gonna shift. This is see, this is x of this point. Look at here, guys, this point, and now we need x of this point. So we have it. Understand what I'm talking about? This is not magic. So now this, as I said, we need L2 multiplied by, as I said, cosine of, remember, theta 1 plus theta 2. Let me do it. Let me select like this. Okay, multiply by theta 1 plus, you get here, not magic, Got here plus theta 2. But theta 2 is what? This M3. So you're gonna have plus yk and 3 because your output is y. See, y3. This is your x. Exactly the same for y. I'm just copying and pasting. See, but you have to change to sine, from cosine to sine. Here gonna be sine, here gonna be sine, and here gonna be sine. See, exactly this term, exactly this term. L2, L1, and I'm gonna make it a different color for God's sake. But here you have to put hold off command, because if you don't, that let me don't do that. First show you, okay? And let me run it now. You want your desirable. Let me change the original. We're gonna have 45 degree, and you want that it goes to 60 degree. That's right. Let me run it. You see, if you don't put hold off it, the name of this is what? The name of this is a stick diagram. It's good for the journal and publications. Okay, understand? So you have what you're gonna do. You're gonna put hold to make a movie. Hold off. After you stick everything with the hold on, at the end of the last thing that you want to plot, you have to put hold off. Now we're gonna have movie of that. Oh yes, you see that this goes to 45 and 45. That's right. And this is 60. This line. See, this is 60. Understand? Yes, guys. Okay. Clear? Okay. So, and you can now, you can say put grid, because so we can make it more visible, huh? Get here, guys. See, this is grid. Now I can change this problem to the famous problem that we name it in the vibration control labs, the double inverted pendulum problem. How? Let me put this as minus 0.5. It's very easy, guys. I'm gonna say the both goes to the upright position, 90 degree, pi over 2. Let us see how it looks like. Oh, this goes here, but this goes here. So, but the problem is that here you have to say 0. Because remember, these are the relative angles that we made. Look at here, guys. See here? So this is this angle. Where are you? This must goes to 0. They both goes to upward position. So the enough is that you say zero. Let me do like that. Pi over 2. Pi over 180. Make it consistent, huh? Now I have a problem with double inverted pendulum. Oh yes. You see? This is a very famous problem in the vibration control things. See what you have the bizarre the control inputs to make that happen. Okay? This goes to, it shows 0, but this 0 means theta 2 means 0 means because of that. That's right, remember? And this is 90. This is with respect to this 0. That's right, this line is with respect to this 0. And that's why they both go to 90. But if you want to make the second link the real 60, you're gonna say this is 45. This is 45. If you want to make it the real 60 with the horizontal line, you have to say 50. Because 15 plus 45 is 16. That's right. Look at here, guys. Look at here. So this is 45 plus 15 degree gives you 16. Understand what I'm talking about? So see, 15 with respect to this. That's right. So 15 plus 45 gonna give you 16. Understand? But if you want to make with respect to the first link, you got to say whatever you want. You're gonna say 60 with respect to the first link. So it's gonna be like that. See? Now this angle is 60. So here we go. Understand? Now if you are out of your mind, it's enough that you make your system underdamped. How? I taught you in the undergraduate control and vibration. See here again? So I'm going to select zeta as 0.5 because your system is underdamped. So your KD, I'm saying it's equal, gonna be 2 multiplied by 0.5 multiplied by omega n. And again, your KP is omega n squared. Again, if I give omega n is 1, your KD based on whatever you designed is 1, and this is 1. Both are 1 now this time. Understand? Understand? I'm giving some number. I'm putting here because your zeta is smaller than 1 is 0.5, so the both must be 1 now this time. Let us do that. The both are 1. Let me see if it works. Yes, see, it oscillates and backs and finally stops. See, now you have underdamped robotic systems. See, overshoot and goes back. See, so what, you're not stupid to do that. Even that you can make it worse. How? I'm just giving I'm KP larger than this. I'm gonna 3 and 3 to make you a complex conjugate pulse. Come on. Oh yes. See, it's still settling down. So this is your U as changing the control inputs, and this is what you get. But we never do that in robotics. Never do that. So officially we are done with the robotic course from the graduate level, guys.